Welcome back to the Physics Bible. In this video we're going to look at CP6, which is the radioactivity section of paper 5 of the Edexcel GCSE. Let's go. And don't forget, you can do this. Okay, first question. What is the approximate size of an atom? What is the approximate size of a nucleus? These two numbers are just numbers which you need to know. There's nothing you can work out from it. You might be asked to just state what they are. So roughly speaking, the size of an atom is about 1 × 10 to the minus 10 meters, and a nucleus is a lot smaller than that. It's actually about, well, it's about 100,000 times smaller. About 1 × 10 to the minus 15. Compare the plum pudding model of the atom to Rutherford's nuclear model. So remember, you can pause the video, have a go yourself, and then check the answer once you've finished yours. So I'm going to go through that in a couple of seconds. Okay. So the two models are the plum pudding model and the nuclear model. So I'm just going to write plum pudding and nuclear. And we'll have two different colours for the key points of this. The plum pudding model came first, so this is the older model, and it was thought that all atoms were a ball of positive charge with negative charge kind of dotted around in it, which is why they call it the plum pudding model, because around the time that this was accepted, plum pudding was a popular dessert, and in the pudding, so that bit there is the pudding, and that represents positive charge, and these bits are negative, and they're the plums. Negative charge. The nuclear model, however, is different in that we now know that the positive charge is actually in the middle of the atom, in the nucleus, along with neutrons, which weren't even discovered at this point, and the negative electrons are on the outside. So we've got the nucleus, which overall is positive because it's made of protons and neutrons, and then we have the outer shells, which are containing the electrons, which are negative. Okay. When we would to write this out, to answer the actual question compare, the word compare in an exam means talk about both, give as much information about both as you can. So here you would just talk about how it was a ball of positive charge with negative charge dotted around in it, whilst the nuclear model has the positive charge in the nucleus in the middle, and the rest of the atom is actually empty space. So those are our two models. Next question. When Rutherford fired alpha particles at gold atoms, most of the alpha particles went straight through. Why? Well, the nuclear model, I've already seen, looks a bit like that. And so if you imagine alpha particles are being fired into the this, there's going to be lots and lots of alpha particles which are really small, like smaller than an atom, because remember an alpha particle is 2 protons and 2 neutrons, so it's essentially the size of a nucleus itself. So you've got something really small being fired at something which is quite large compared to this. An atom obviously isn't large, but the nucleus is very, very small. Nucleus is possibly the size of the alpha particle. So most of them are going straight through. Why? We said it before. That area of the atom is empty space. So you'd be expected here to write about how most of the atom is empty space, and so the alpha particles that get fired at it will just go straight through because they won't hit the nucleus. About 1 in every 10,000 bounce back. Why? Well, we're going back to this. Obviously, the vast majority are going to go straight through in this massiveness of empty space. Lots of empty space here. If we were to do this to scale, it would be like the nucleus is about the size of a tennis ball, and the outside of the atom would be 1,000 meters away. So everything in between that would just be nothingness. So why was it only 1 in 10,000? Nucleus is very small, so only 1 in 10,000 alpha particles hits it. Charge of an alpha particle is positive. Charge of a nucleus, we've already said, is positive. And so every now and then you're going to get an alpha particle coming in and getting so close to the nucleus that it actually gets repelled and bounces back. And that's what it means by that. Complete the table below. So the subatomic particles as part of the atom, we've been given 1 and we've got 2 more. One begins with an N, one begins with an E. Location, so whereabouts are these particles found, and what is their relative charge and relative mass. So I'm just going to give you a second, see if you can fill in the areas of the table on your own. Pause the video and give it a go. Right, subatomic particles. Proton, neutron, and electron. Those are 3 subatomic. Sub means inside or within or underneath. So subatomic means these are like inside the atom. They make it up. So the proton is in the nucleus. The neutron is also in the nucleus. Let's add a neutron to our diagram. Let's add 2. There we go. So we've got 2 protons, 2 neutrons. And then finally the electron those are in the outer shell. Those are on the outside. So protons and neutrons in the nucleus, electrons on the outer shell. Everything in between, empty space. The charge, a neutron, is neutral, and an electron is -1. It's the opposite to the proton. So to have a neutral atom, you can see here we've got 2 balls of positive charge, so 2 protons in the nucleus, and we've got 2 electrons in the outer shell, so the overall charge of this atom would be 0. What about the relative mass? If the mass of the proton is 1, then the mass of the neutron is also 1. They're pretty much the same size. The electron, however, is much, much smaller. It's about 1 in 1,835, so it's nearly 2,000 times smaller than that. Negligible means it's not even worth comparing, really. It's so much smaller than these two that you could essentially call it 0. It's not quite 0 because it does have a mass, but it's very, very small. we've got a chemical symbol here. C is for carbon, and we've got two numbers, 12 and 6. The question here is, which number is the mass number, which number is the atomic number, how many protons are there in this carbon, and how many neutrons are there? Have a go yourself and then check the answers in a second. Okay, so after pausing the video, hopefully you've said that the mass number is 12, the atomic number is 6. Let's go from there. So that is the mass number. I remember that because the number is massive compared to the one underneath. In other words, the biggest number is always the mass number, the massive number. And the bottom number is the atomic number, because that's the number that tells you which atom it is. Now this top number could change, but as long as that bottom number stays as the number 6, then this will always be carbon. So you could have an isotope of carbon like that, it would still be carbon. But as soon as we go up to 7, we now have nitrogen. We've got a different element. That bottom number tells you what atom it is, and so it's called the atomic number. And the atomic number is the number of protons. So the atomic number is 6, so this must have 6 protons. What about the number of neutrons? That mass number is the number of protons and neutrons. So if there's already 6 protons and the mass number is 12, then it's the difference between the two, 12 minus 6. So actually there's 6 neutrons as well. What about if we did it for this isotope? So for this one, there are 6 protons, but how many neutrons are there? Well, there's still 6 protons, but the number of neutrons added to the number of protons has to give 14. So 6 add 8 is 14. So in this version there must be 8 neutrons. In this nitrogen there are 7 protons. Therefore there must be 7 protons, but also what makes 14? 7 add 7. So there's 7 neutrons as well. Complete the symbol for the made up element Persium. It's got 72 protons and 90 neutrons. See if you can fill in those two numbers. Okay, well let's start with the protons. We know that the protons, that is the atomic number, which is the bottom number. So that would be 72. And the top number is the mass number, that's the number of protons and neutrons. So 90 plus 72 is 162. So Persium has 72 protons and a mass number of 162. Give an example of an isotope of Persium. Well, an isotope has the same proton number. Okay, so it's got the same number of protons but a different number of neutrons. So as long as you put 72 on the bottom, then this isotope of Persium, you could put any number near 162, so I don't know, 165? That would be an isotope of Persium. As long as the proton number, the atomic number is the same, it's the same element. If we were looking at something which was 73 and 165, it wouldn't be Persium. Maybe it would be another made up element, Davidium. Next, explain what ionisation is by using the diagram below. So we've got an atom, a nuclear model which has 3 protons, 3 neutrons, and 1, 2, 3 electrons. We've got to include in our answer the charge of the atom at the moment, what an ion is and how does the atom become an ion. Now that's been split up for you, so have a go yourself and then check back on the video. First of all, ionisation is what we call it when an atom becomes charged. How does an atom become charged? It has to have a different number of protons to neutrons. Wrong. Even I make mistakes sometimes. It has to have a different number of protons to electrons. Protons are positive, electrons are negative. So at the minute we've got 3 positive protons and we've got 3 negative electrons. If we recall our table, we said that the charge of a proton is +1 and the charge of an electron is -1. So that means we've got a +3 charge from the protons and a -3 charge from the electrons. So what is the overall charge of the atom at the moment? 0. And that is what we call an atom. Now ionisation is where the number of electrons gets changed and therefore it's not balanced out with the protons. So an ion is a charged particle or a charged atom. At the moment, the charge of our atom is 0, therefore it is not an ion. So if we know that an ion is a charged particle or atom, then we're going to have to change this number. How does it become an ion? The electrons are the key to this answer. An electron is either added or removed from the atom. So if we add or take away an electron, we're either going to end up with a bigger negative number such as -4 or a smaller negative number such as -2. The proton number is always going to stay the same because it's locked up inside the nucleus. So if we've got the same number of protons but we change the electron number, let's say we have an extra electron, then we've got -4. -4 plus 3 gives us an overall charge of -1. -2 and +3 gives us an overall charge of +1. So that's 2 ways that you can create an ion, either by adding an electron to the atom or by taking an electron away. How can we actually do that? One way is to bring in some energy, such as an ultraviolet particle of light, and if the electron absorbs it, it has enough energy to then leave the atom, and so we forget that it was ever there. Let's block that out. There we go. And now we can see that the atom has 3 protons, 3 neutrons, but only 2 electrons. So the charge of the electrons is -2, the charge of the protons is still +3, neutrons is 0, so the overall charge +3 -2 is +1. Therefore, by getting rid of that electron, we've created an ion, a charged atom. Next, name 3 sources of background radiation. So 3 places where background radiation comes from. Check your revision guide, see if you can pick out 3. Okay, so 3 sources of background radiation. There's about five or six kind of obvious ones to go for here. My top three are radon gas. Now radon is a gas which is present in the atmosphere, so it's in the room that you are at the minute. It's a very low amount, but it is a radioactive gas, but it's in our atmosphere, and so that contributes to emitting alpha particles all the time. It's just a really low amount. Another one that I like is cosmic rays. So we actually get exposed to radiation from particles that are flying towards the Earth from outer space, and when they reach the atmosphere, they can decay and they produce radiation. Another one is medical sources such as X-rays, you know, that's going on in hospital, but also radioactive waste from chemotherapy, from cancer treatment. So we're producing radioactive waste in hospitals every day, and that ends up you know, an extremely low level, but that kind of ends up as part of the background radiation that's always there. Other ones you could have had are nuclear fallout from bombs. When bombs get tested, nuclear bombs, that radioactive material ends up in the atmosphere, and until it decays, it's always going to be there. It's, you know, it can't just disappear. So all of that radioactive material ends up in the air, and it gets spread around the world. We can also have rocks from the ground. Certain granite rocks, for example, can be gamma emitters. And finally, even some food is radioactive. If you don't believe me, look up radioactive bananas. Bananas contain an isotope of potassium, which is good for you in small amounts, but it's actually a very, very, very low level radioactive substance. It's not dangerous. Don't stop eating bananas because of this video. Next, what is the name of the device that measures radiation? So this is referred to as a GM tube, but we want to be able to write the full name, which is the Geiger-Müller tube. The Geiger-Müller tube, named after the two scientists who carried out the experiment to prove that the atom looks like this. What causes the device to detect radiation? Well, the Geiger-Müller tube, as the name suggests, is a tube. It has a rod in the middle which is highly charged. It's positively charged, and the outside of the tube is negatively charged. Now, the gas that's inside the tube is neutral until something like alpha comes along. Let's use green. So there's my alpha particle. When it goes into the tube, it actually ionizes the gas. So it causes the gas to have a charge. Just as we talked about here. The alpha particle comes in and it rips an electron off an atom in the gas, which then makes the gas positive, and then the gas gets repelled from that middle line. It goes towards the negative, and you get a little current, a little spark. And so every time an alpha particle comes in and ionizes the gas, we get a little spark because of the charged gas, and then it counts it on the counter. So you start with 0, and then you hear click, and we have 1, and then you might hear click, click, click. That's counted another 3, so you end up with 4. And you can leave that running for a while, and every time you hear a click, it's because a little spark's happened inside because of the gas in the tube becoming ionized. If the background count is found to be 20 counts per minute, and a rock sample is measured at 130 counts per minute, what is the actual count rate of the rock? So let's do what we normally do and pick out the numbers in the question. So the background count is 20 counts per minute, and the rock, so the rock sample is 130 counts per minute. When we use the Geiger-Müller tube to measure the rock sample, so there's the rock and there's the Geiger-Müller tube. The Geiger-Müller tube is picking up radiation from the rock, but it's also picking up background radiation. So how do we find out how much the rock is actually producing? Well, we have to take the total amount, which is 130 per minute, so that's what it records on the Geiger-Müller tube. But earlier on we tested to find out what the background count was, which was 20 counts per minute, and so if we test a rock and get 130, we'll have to remember to take away the background count. So you do the total minus the background. That'll give you the sample number. So the rock is actually only producing 110 becquerels. Oh, sorry, that's counts per second. So counts per minute. Becquerels is the unit of activity, which is actually the amount of counts per second, but our question says counts per minute, so I can't use that. So the rock's 110 counts per minute. Next, what are the names of the 3 types of radioactive decay? Alpha is positively charged. Beta is negatively charged. And gamma doesn't have a charge. In this table we have to fill in the name, put the symbol for the type of radiation, give some information about the particle, so in other words, what is an alpha particle, what is a beta particle, and finally, what's the charge of each of them. Well, I've just given you a lot of hints, not just there, but also in these previous questions. Let's see what you've picked up. See if you can fill in the table yourself and check in a second. Okay, so first one is alpha, the second one is beta, and the third one is gamma. The symbol for alpha is done for you. The symbol for beta, well, there are 2 types of beta decay. One produces a negative electron, and we call that beta minus. And the one that produces a positron is actually positively charged. So I'm going to use the red for this, and we call it beta plus. Gamma has the Greek letter gamma as its symbol, which is that. You can see the alpha symbol is that one on its side, vice versa. What do we know about the particles? Well, an alpha particle is made of 2 protons and 2 neutrons, and I'm going to draw around them. 2 protons and 2 neutrons. This is just 2 protons and 2 neutrons that get spat out of a radioactive atom. It comes from the nucleus and it gets ejected, so it loses 2 protons and 2 neutrons. In beta, it's a little bit more complicated because, one, people often see the electron and they think, oh, electrons, well, they're on the outside of the atom, so it must have come from here. That's not correct. Beta decay is still nuclear radiation, and it's called that because it comes from the nucleus. Well, how can we get electrons from the nucleus? I've just been telling you that there's only protons and neutrons in the nucleus, and the electrons are on the outside. The reason why an electron can be created in the nucleus is because there's a change. The particles in the nucleus change, and when they do that change, they give out one of the beta particles. So for beta minus decay, we actually have a neutron changes into a proton, and when it changes into a proton, it gives out a beta minus, a negatively charged electron. For a beta plus change, the change is slightly different in the fact that it's the other way around, that a proton changes to a neutron, and when it does that, it creates a positron, a positively charged particle. For gamma, gamma doesn't have any mass. It's like a particle of light, but it's very, very, very high energy light, and we call these little particles of light photons. The charge, +2, because it's got 2 protons. The neutrons are neutrals, so the overall charge is +2. For beta, the charge of beta minus is -1. The charge of beta plus is +1, and the charge of a gamma photon is 0. So there's our summary table of the 3 types of nuclear radiation, alpha, beta, gamma, but remember there's 2 versions of beta that we've got to be aware of. 63, we've got alpha, beta and gamma again. It's given us some information. Moderately ionizing, very ionizing, weakly ionizing, and a few meters in air, a few centimeters in air, or travels forever in air. What we have to do in this question is match up alpha, beta and gamma, and we've got to connect them with lines. So for example, alpha, I need to draw a line from alpha to that one, or to that one, or to that one, and then once I've drawn it to there, I'm going to follow it and go to that one, and that one. So which ones go with which? I'll give you a clue. The bigger the charge of the particle, alpha, beta or gamma, the more ionizing it is, because it's got more charge, so it's more likely to take electrons off the atom. The more charge it has, although it's more ionizing, it actually means it can't travel as far, because it won't get very far before it starts ripping electrons off something. So see if you can match them up yourself, and I'll go through that in a couple of seconds. Okay, so alpha has the biggest charge, +2, therefore it is the most ionizing, so it is very ionizing. Alpha is actually the most dangerous inside your body. Because it's the most ionizing, it means that it can actually disrupt the DNA in your cells, and that can cause mutations and lead to cancer. But because it's very ionizing, it can only actually travel a few centimeters in air. It can't travel very far. So if there was an alpha source in the room next door to me, I would actually, although I'd be pretty concerned that there was a radioactive substance in my house, I wouldn't actually be that concerned that I'd suffered any damage from it. The only way that I could actually be damaged from it is if I ate it, or if it was a gas, if I breathed it in. Beta has a charge of -1, which means that it's moderately, that means kind of average, like a little bit, not too much, not too little, just a moderate amount. It's moderately ionizing, and because of that it can travel a few meters in air. Finally, gamma has a charge of 0. This means that it is very weakly ionizing, so it's not likely going to take electrons off an atom. The only way it can do it is like we talked about before, if a photon of gamma actually directly hits the electron, gives it all its energy, and then the electron leaves. The chances of that are pretty low, which is why gamma sources are going to be dangerous only if there's lots and lots of gamma particles. Because it's weakly ionizing, it means that it can travel pretty much forever in air. Air is not going to stop gamma because it doesn't ionize things, so there's nothing to kind of slow it down. So what materials are going to be able to stop these three types of radiation? We need to know these off by heart. Alpha is stopped by paper, beta is stopped by aluminium, and gamma is stopped by thick lead or thick concrete. Complete the following decay equations. These equations look complicated, but actually all we're interested in is the numbers along the top and the numbers along the bottom. Whatever you get on this side of the arrow, you have to have the same number of protons, you have to have the same number of particles as you do on this side of the equation. So let's look at what's happened. We've got an element which has 226 protons and neutrons. It has 88 protons. The element that it forms has 86 protons and 222 protons and neutrons. So there's something missing. We've lost particles. Let's see what numbers they are. Well, they go from 226 to 222. That must mean that the answer has a mass number of 4, and the bottom number, 86 plus something, equals 88, and that's 2. Now, the particle, which has 2 protons, but a total of 4 particles in total, 2 protons, 2 neutrons, that's our alpha particle. And so that would be the missing particle. See if you can do the next two on your own. We've already been told this is beta, but can you work out what numbers have to go for the mass number and the atomic number? And this one, I'm telling you that it is alpha decay. So can you work out what the missing element is? Okay, so this first one, we have iodine, xenon, and the beta particle. On the top, you can see on the left hand side of the arrow we've got 131 mass number, but xenon actually has 131. So up here is actually a 0. The bottom number is 53. Xenon has 54, so that number, did you get it right? It should be -1. So that is beta minus decay. The next one, we're told it's an alpha decay. So what I would do is I'd actually put that in first. And we know that an alpha particle always has 2 protons and 2 neutrons. So what's missing? Well, on the top, 216 minus 4 is 212. On the bottom, 84 minus 2 is 82. And therefore, what element has been formed? What's the new nucleus? 82 protons. If you check your periodic table, you'll find that that is lead. So the polonium has changed into lead and it's given off an alpha particle. The 2 numbers there add up to that one, and the 2 numbers there add up to that one. Take your answer to C, which is this one, and write an equation to show what happens if it then does beta minus decay. There's an example of beta minus decay. So see if you can write out the whole equation by yourself, starting with that element. If you really want to find out what it changes into, you're going to have to check your periodic table. Give it a go anyway and see if you can get the numbers on the top row and the bottom row correct. So because it said that it's going to do beta minus decay, the beta minus symbol is always 0, minus 1. So I've just added that in straight away and then thought, okay, what does the top row, what does the number have to be here to make the top row correct? And because it's 0 there, it means that my first number is the same. 212 and 0 gives 212. What about the bottom number? Something added to -1 gives 82. Well, that is 83. 83 plus -1 is the same as 83 minus 1. And that gives us bismuth. So we've got another change of element. Okay, activity. You'll have heard this word before when dealing with radioactivity. And the activity is a definition, it's a key word, it's a word that you might have to actually give a definition for in the exam. And that's what this question's asking. Define means tell us what it is. It also says state the unit of activity, and I accidentally give the unit earlier on in the video. Pause the video, see if you can do your own definition of activity, and see if you can remember the unit. The definition of activity is the amount of radioactive decays per second. That's the important point, per second. It's a rate of how quickly decays are happening. So if something has a high activity, it means that lots of atoms are giving out alpha, beta or gamma very quickly. Highly active substances are generally more dangerous to people because it means you're getting a high dose of alpha, beta or gamma in a small amount of time, and that's dangerous. The unit, if you remember, I actually wrote BQ and BCQ. I normally have to check how to spell this, but even though I did know it, I always check BCQ. It's called the becquerel. It's named after a French scientist, Henri Becquerel. And 1 becquerel means 1 decay per second. 10 becquerels means 10 decays per second. So what happens to the activity of a substance if you burn it? So if we've got a rock, let's say it's a lump of granite which is radioactive, it's given out gamma. So here's the gamma, there it is, and then we come along and we throw it on a fire, and the fire burns and it gets really hot. What happens to the activity? And the answer is nothing. We cannot change the radioactive properties of a substance by doing anything chemical with it, and burning is a chemical reaction. Chemical reactions affect the electrons on the outside, but they don't affect the nucleus, and it's the nucleus which is actually going through the radioactive decay process. So you can burn it, you can put it in acid, you can blow it up, grind it up, try and put lots of other chemicals on it, but you will never stop it being radioactive. And that's why radioactive substances are so dangerous. I mean, even if you ate a radioactive substance and you digested it and then you died, then your body would be radioactive. And then if you were buried 100 years later, your body may still be radioactive. In 1,000 years, your body may still be radioactive. The radioactive atoms only go away once they've actually decayed and given out an alpha, beta or gamma. And so if you've got millions and millions of them in your body, it might take a very, 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 very long time before you've actually not got any radioactive substance in your body. The half-life of a substance is the something, something, something for the activity to half. Pause the video and see if you can work out what that is. Half-life is another definition term that we need to know. We need to know that activity is the amount of decays per second, and we need to know that the half-life of a substance is the time it takes for the activity to half. So if we have 100 becquerels and we measure it after 2 minutes and it falls to 70, and then another 2 minutes and it falls to 50, and then another 2 minutes falls to 30. The time it takes to go to half, well, it was 2 minutes, so the half-life would be 4 minutes. Another way of looking at it is that it's the time it takes for the number of radioactive atoms to half. So if you had 100 radioactive atoms and as if you could see them, it would be the time it takes for half of the radioactive atoms to decay. You'd then be left with half the amount. The half-life would still be the same, and it would be the time it takes for half of the remaining atoms to decay. So if you had 100, it would be the time it takes for 50 to decay, so it goes from 100 to 50. It would then take the same amount of time to go from 50 radioactive atoms down to 25. If Persium has a half-life of 5 years, okay, before we even read on, what does that mean? Well, first of all, Persium doesn't exist, so sorry about that, but if it did, it's got a half-life of 5 years. That means it's going to take 5 years before the activity is going to drop to half, or it's going to be 5 years before the number of radioactive atoms of Persium is going to drop to half. The question is, how many half-lives would have passed in 20 years? Now, I also do my own little diagram for this. Here's my starting point. 5 years passes, which is 1 half-life. Another 5 years passes, which is another half-life. Another 5 years passes, which is another half-life. And another 5 years passes, which is another half-life. 5 years, 10 years, 15 years, 20 years. So that's a total of 20 years, which means that a total of 1, 2, 3, 4 half-lives have happened in that time. If the question was the half-life was 2 years, then how many half-lives would have passed in 20 years? See if you can figure that one out yourself. So if the half-life is 2 years, how many half-lives in 20 years? Well, it would be how many 2 years fits in to the 20 years, and that's 10. So you'd get 10 half-lives. So if the half-life is 2 years, then the amount of radioactive atoms will actually have halved 10 times. But if the radioactive material has a half-life of 5 years, then in that 20-year period it will only have halved 4 times. So this one will now be less dangerous than the one that's got a longer half-life. If the activity of persium is 1,200 becquerels, what will the activity be in 20 years? Well, we worked out that there's 4 half-lives have happened in 20 years. If the activity is 1,200 to start with, we want to know what the activity is going to be like in 20 years, which is 4 half-lives. See if you can get an answer on your own. Okay, so we start with 1,200 and then we have 1 half-life which halves it to 600 becquerels. So that's 1 half-life. 2 half-lives takes it to 300. 3 half-lives takes it to 150. 4 half-lives takes it to 75. So 4 half-lives will half it 4 times. Half that number, get 600. Half 600, get 300. Half 300, get 150. Half 150, get 75. So what will the activity be in 20 years, 5 years, 10 years, 15 years, 20 years? Final answer, 75 becquerels. If there's 10 million atoms of persium in the year 2018, how many will there be in 2033? Let's recap what we've got. The half-life of 5 years. There's 10 million atoms, but the half-life can be the time it takes for the number of radioactive atoms, 10 million, to half. So after 1 half-life it's going to drop to 5 million. But we need to know how many half-lives there are between 2018 and 2033. The difference between those 2 years is 15 years. So 15 years passes from 2018 to 2033. How many half-lives is that? 1 half-life is 5 years for persium. So that's 3 half-lives. So we start with 10 million. 1 half-life takes us down to 5 million. 2 half-lives takes us down to 2.5 million. And 3 half-lives takes us down to 1.25 million. We start with 10 million, 15 years, 5 years for a half-life, 1 half-life, 2 half-life, 3 half-life. Final answer, we'd have 1.25 million atoms. You can obviously use a calculator to half these numbers if you wish. In fact, I recommend it if you're not 100% confident with that. We're nearly finished, I promise. Look, the next page is empty. So this is the end of the last topic in the paper 5 of the Edexcel GCSE Physics. Using this graph, find the half-life of the sample. So I'm going to zoom in and I'd like you to pause the video and work out the half-life for yourself. Looking at the side, the y-axis tells us the activity, and along the x-axis the time in years. We know that the half-life is the time it takes for the activity. Let's go back. Where is it? The half-life of a substance is the time it takes for the activity to half. So we look at what the activity is. It starts at 1000, and so we want to know how long it takes to drop to 500. So I'm going to draw a line along from 500, and I'm going to draw it down from there, and we find that it takes 4 years to half. so the half-life is 4 years. We can prove that by going, okay, well what about if this didn't happen? What about if the activity starts at 500? Then if it's true that the half-life is 4 years, then in another 4 years it should have dropped from 500 down to 250. So let's check that. We go up to 250, down to 250. So how long has it taken to go from 1000 to 500? It's taken 4 years to get to that much. It continues dropping. How long until it drops to 250? Another 4 years. So there's the first half-life, there's the second half-life. So after 2 half-lives we'd be down to 250 becquerels, and it would take 8 years. Okay. Next, explain the difference between irradiated and contaminated. I suggest you pause the video and look in your revision guide for this. You need to know the definition of those two words. What does irradiated mean? What does contaminated mean? See if you can find it, and then see if you are correct. Come back to the video. Pause it now. Okay, so the definitions. Let's start with irradiated first. When something is irradiated, it means that something has been targeted by the alpha, beta or gamma. Now this can be accidental or it can be on purpose. For example, in hospitals they often take scalpels, for example, and rather than clean them with soap and water, these things can be used and be full of bacteria. So what they'll do is they'll actually blast it with gamma rays, gamma radiation, and that will kill all the bacteria because the gamma rays have so much energy. This process is called irradiation. Now it doesn't have to be gamma. If there was an alpha source, there's alpha and then there's U, then if you were extremely close to the alpha source, so close that the alpha particles could reach you, then that would also be classed as irradiation. So it's when the alpha, beta or gamma actually affect living cells. Contamination is different because it actually talks about the movement of the radioactive substance. So, for example, you may work with radioactive materials. You go to work and you don't follow the rules, and you end up with radioactive material on your suit or on your clothes. When you leave work, we could say that you had been contaminated. You have transferred some of the radioactive substance onto yourself. You could also contaminate other things, such as your sandwich. You could maybe be, if you touched a radioactive material, it could contaminate your hands, and then if you touch a sandwich, you could contaminate your sandwich. So it's the movement of the radioactive substance between different things. If you are contaminated and you leave work, then it's safe to say that you're also being irradiated, because if the contamination is on you, then you're going to be alpha, beta and gamma may actually be affecting your living cells. Finally, explain how the following precautions reduce exposure to radiation. Exposure means how much you're basically being affected by it. So how do you reduce the danger of radioactive substances? And precautions is about what you do to reduce it, to make it more safe. So why do we handle sources with tongs? Often we'll actually have long metal tongs and the radioactive source will be at the end. Why do we do that? Why do we store sources in lead-lined containers? So we've got tongs which hold the radioactive substance, and we've also got lead-lined boxes, so basically the sides and the top and the bottom are made of lead. Have a go yourself and check the answer in a couple of seconds. Okay, handling sources with tongs, we do that to increase the distance between ourselves and the radioactive source. The further away you are from something radioactive, the less chance there is of it, the less chance there is of you being irradiated, the less chance there is of it damaging your cells. Why do we store them in lead-lined containers? Lead stops alpha, beta and gamma radiation. Now, if it was gamma in there and it was only thin lead, then we might get some gamma coming out. But in general, you wouldn't store a gamma source in a little box like that anyway. So by putting alpha and beta in that box, if it's got lead on the outside of it, then alpha and beta particles are not able to get out. So we store sources in lead boxes so that it stops the radiation, and so people don't get irradiated when carrying the box. Okay, so that's it. This one was quite a long one, I know, but it's quite a large topic and it's one of the more difficult ones. It's the last one in the paper. I hope you found it helpful, and no doubt I will see you in my next videos, which will be about paper 6. So see you then, and good luck.